This is the summary video for what Chapter 5 is about, and I call it a tree map because it goes into the branches of what our unit is about. So Unit 5 is all about using derivatives to analyze functions, or what the first and second derivative can tell us about our function. The first thing we did with Unit 5 was the mean value theorem. First of all, in order to use the mean value theorem, you must have a continuous on the closed interval. Remember that to be continuous at the endpoints, the function, the limit just from one direction has to match. And then you also have to be differentiable on the open interval. You can't be differentiable on a closed interval because it's hard to do a derivative of an endpoint, so that's why we only have to be differentiable on the open interval. Together, those two rules are called smooth. A continuous differentiable function is one that when you sketch it, it's all smooth and curvy. It doesn't have jagged edges or cusps or discontinuities. So in order to use it, make sure that you have some way of justifying that you have a continuous differentiable function. And what it says is that if you take the derivative, or the instantaneous rate of change, there exists some point on the interval such that that derivative is equal to the average rate of change. And the conclusion of the mean value theorem says that C is on the open interval. So if you find a C that's on the endpoint, that's cool, but it doesn't satisfy the conclusion of the mean value theorem. The conclusion of the mean value theorem promises you that there will be a C on the open interval. So on the interior of that interval, you will find a C. It doesn't tell you how many C's you will find. It doesn't make it easy to find the C, but it promises you that one exists. Graphically, what that means is you have this smooth function. There is a point here at A and a point here at B, and I can calculate the average rate of change or the slope of the secant line between A and B, and I guarantee that there will also be somewhere on the interior of that interval a point where the tangent line has that same slope. The other thing we did in this Unit 5, and we spent a lot of time with this, was we did maximums and minimums. So there were 3 different tests that we looked at for maximums and minimums. The first test I'm going to talk about, although not the first one we learned, is called the candidates test. The candidates test says, hey, the only time you can have a maximum and minimum is at critical points and endpoints. So let's just compare y-coordinates at critical points and endpoints. When you're using the candidates test, make sure you also include endpoints. That's a common mistake not to include those. And what you're comparing is you're comparing y-coordinates. So you're comparing f. So you're comparing your y-coordinates. You're not using your derivative at that point because you want to know which one has the largest or smallest y-coordinate. Definition of critical point, just to remind you, is where f prime equals 0 or where f prime does not exist. The other tests are using the sign change on the first derivative, so that's the first derivative test. The first derivative test is the one where we draw a number line to help ourselves, and we're on that number line we're looking at the value of f prime in between our critical points. We know that f prime doesn't exist or is equal to 0 at the critical point, but we look around the critical point, and let's say that we have more than one critical point. So we could have that f prime is positive for values less than c, positive for values between c and this other c, and then negative after that. And that tells us that our function is increasing, maybe flattens out a bit, and then continues to increase and then decreases. So the first derivative test would tell us that there is a maximum value at c sub 1 because the sign change on f prime. I also want to remind you that this number line, which is really handy for you, it's really good for you to look at, does not count as a justification. You have to write that sentence out in words, and make sure when you are writing that sentence out in words, you don't say things like it or the graph or the function. Don't use those kind of words. Instead, talk about f or f prime so that you're very clear. So f prime changes from positive to negative at c sub 1. So f of c sub 1 is a max. Use very clear language, and also remember that the c and c sub 1 are x coordinates, but your maximum value will be the y coordinate of the function. So that's the first derivative test, and then we also had the second derivative test. And the second derivative test also uses critical points. So you still need to find your critical points, but so it says you've got the kind of critical point where the derivative is equal to 0. So you have a horizontal tangent line, and then you can check the concavity to see if the concavity is concave up. I should write a 0 there, not the word up. So if your function is concave up, then you know that you have a up like a cup and a horizontal tangent line, so you have a minimum. And then if your second derivative is negative, then you have a maximum. And the other thing is that if your second derivative is equal to 0, then you can't use the second derivative test. It doesn't tell you anything. It doesn't tell you you have a neither. It doesn't tell you you have a minimum or a maximum. You really need to use a different test. The other thing we did with maximums and minimums is we did a whole bunch of work with optimization problems. Optimization problems are really just applications of finding the maximum and minimum. A big thing about optimization problems is that you start by figuring out what your restriction is. Your restriction is what's keeping you from covering the earth with whatever you're building, or choosing teeny numbers if you're trying to minimize something. And then you solve that restriction for y. And then you have to write the function that you are trying to optimize. So the thing that you're trying to find the maximum or minimum. When you write that f of x equation, don't think about the restriction. Just think about what is the thing that I'm trying to optimize. You will have x's and y's in that. You use the restriction to get rid of the y. And then you do your calculus that we just learned in this unit to figure out where the maximums and minimums happen. So optimization is really just an application of this process of finding maximums and minimums. We also talked in this section about concavity. So a function has slope, but it also has concavity. When your second derivative is less than 0, then you have a concave down like a frown function. So that would be this part. And when your second derivative is greater than 0, then you would have a concave up section of your graph. Sometimes the concavity can be subtle, so it might not be totally obvious where that happens. In this section, we also talked about inflection points. inflection points have two conditions. You must have your second derivative is either equal to 0 or does not exist. It's a little bit like a critical point, except you're looking on the second derivative rather than on the function itself. And in addition to that, it doesn't count as an inflection point unless you also have a sign change on f prime. It is essential, if you are justifying an inflection point, that you mention the sign change. An inflection point is not just when the second derivative is equal to 0 or does not exist. There's also a sign change. The other thing is, remember that an inflection point is an ordered pair. So that would be a point, so you would have an x-coordinate and the value of the function would be the y-coordinate. Same thing for critical point. If I say critical point, I want an ordered pair, and we use f to get the y-coordinate. Then we talked about implicit functions and what you can tell about relations, what you can tell about an implicit relation by looking at its derivatives. So we know how to figure out dy dx with an implicit derivative. If you know dy dx, usually it's a fraction with a numerator and a denominator. If you I don't know why I feel like I need to write out that whole word. I can't even spell it. Let's just call it a dem. If you know your dy dx as a fraction, then when you set the numerator equal to 0, then you have a horizontal tangent line, or dy dx is equal to 0. That is also a critical point because you have your derivative is equal to 0. If you set your denominator equal to 0, then you have a vertical tangent line, and you also have a critical point. So so those are useful pieces of information. With implicit differentiation, because you can't figure out a sign change because both x and y are changing, you're going to want to use second derivative test. And the reason you want to use the second derivative test, well, I already said it, is because both your x and y are changing, so you can't say you have a sign change at this x-coordinate because y is also changing. And when you use the second derivative test, you're going to take that second derivative, and you're going to make sure that as soon as you take the second derivative, you plug in your x-coordinate, you plug in your y-coordinate, and you plug in your first derivative immediately. So you're not going to do a bunch of algebra on that second derivative. You're going to plug in your values right away after you take the second derivative. Not before you take the second derivative, but after. Right after, plug in numbers. Numbers are easier for us than algebra. We don't want to spend a lot of time messing with algebra if we have numbers that we're going to plug in anyway. All right, that is a quick summary of Unit 5, and I'll see you tomorrow.